All right, moving on. So getting into linear functions, right? Linear, the definition of linear is one straight line, right? Hence the name linear, one straight line. So we're just getting rid of those functions that are not on one straight line. So this is curved. Hold on. Okay, so function 1 is curved, so it's not linear. Function 2 is a straight line, so that is linear. Function 3 is a straight line, so that is linear. And function 4 is curvy, so that is not linear. Okay, moving on to linear on, these are more graphs. So function number 1 has two straight lines with a bend in the middle. Because of the bend in the middle, the right corner in the middle, this is not linear. Number 2 is a straight line, so it's linear. Number 3 has a curve, so it's not linear, and this one's definitely not linear. Okay, moving on to 12. Okay, so what does a linear equation look like? Well, a linear equation, for example, my pen stopped working. Hold on. A linear equation like y equals 6x plus 7, something like that. A linear equation has the variable. We're looking at the variables of the exponents of the variable. I'm sorry. We want the exponents of the variables to only have exponents of invisible 1, right? So we know that if we have like any sort of base, any constant or variable where there's not like a written exponent, we know that it has an invisible exponent of 1. Okay, this means that we do not want any variables in the exponent, nor do we want them in the denominator. Okay, so it is linear as long as it has an invisible 1 as exponents. That means in order to have that, your variables also cannot be in the exponent or in the denominator of a fraction, right? So equation A has the x has an exponent of 2, so that is not linear. In equation B, y has an invisible exponent of 1, so that is linear. In C, y has an invisible exponent of 1, and x has an invisible exponent of 1, so this is also linear. And then same thing for D, so it's linear. All right, going on to 13. Same thing. Let's see. So we're looking for invisible exponents of 1. So in A, we have an invisible exponent of 1 for the x, so that is linear. B, we have the same thing, invisible exponents of 1, so this is also linear. Same thing for C, linear. And lastly, in D, we have a variable in the denominator. So since we have a variable in the denominator, the exponent is not, the invisible exponent is actually not 1. Well, it has an invisible exponent. I'm not going to go too deep into it. It would have an invisible exponent of -1, so this is not linear. Okay, going on to 14, same thing. We're determining linear, but from like points and tables. Now, a linear function, we can tell that points are linear because they have a constant rate of change. So what does that mean? I'm going to look at all the x values and see how the x values are changing. And I want all of the x values to be changing at the same rate by the same number, either adding by the same number or subtracting by the same number. And then I also want the same thing for the y values, okay? So looking at the first, going from x to x to x, the x is going up from 5 to 8, that goes up 3. From 8 to 11, that also goes up 3. And from 11 to 14, that also goes up 3. Of course, we can always work backwards in case you did not know that immediately. You could do 14 minus 11, and then 11 minus 8, and 8 minus 5, and you would see that those are all changing by 3. Now I just have to check the y values. The y values are changing from -2 to -6, that's going down by 4. From -6 to -9, that went down by 3. And from -9 to -10, that went down by 1. So this one, since the y's are not it's constantly changing by the same number, this first function is not linear. Okay, we're going to do the same with function 2. So I'm going to first analyze the x values. So the x values from -3 to -2 went up by 1. From -2 to -1, that went up by 1 as well. And from -1 to 0, that went up by 1. Now I'm going to check the y values. The y values from 4 to 4, that changed by 0, right? We didn't actually add anything to it. From 4 to 4, that went up by 0. And 4 to 4, that went up by 0, right? Didn't actually change. So since the x's were the same, like changing at the same rate, and the y's were also changing by the same rate, we would say that this one is linear. Okay, now we're going to do this for the bottom. Okay, so we're going to first analyze all the x's, and then we'll analyze the y's. So the x's, should I do this backwards? Let me do this backwards just in case. So I can subtract. I can do 5 minus 2, that is 3. That's going down by 3. I can do 2 minus -1, that is also 3, going down by 3. And -1 minus -4, that is also 3. Okay, so you can go forward or back, right? A right is a right. Okay, and now I'm going to check the y's from 3 to 5, that went up by 2. From 5 to 7, that went up by 2. And from 7 to 9, that went up by 2. So that is all going to be linear. And last one, 2 to 6, that's 4. Plus adding 4. From 6 to 10, that's adding 4 as well. From 10 to 14, that is adding 4. Lastly, we got from -5 to -6, that's going down by 1, and down by 1. but this one is also linear. Okay, 15 is the same thing, and 17, we get into function notation. Yay! Okay, so function notation, we have learned function notation in class. Function notation is just a fancy way, function notation is the notation f of x, okay? So that's how we say that, f of x. F of x is just a fancy way of writing y, okay? And that's all we really need to know, right? So in this example, we got f of 2. They replaced the x in the f of x with 2. So that's what they want you to do. They want you to figure out what f of x is. So find y when x is 2, right? So how do I know what y is when x is 2? I'm going to go to my graph. I'm going to go to the x-axis. I'm going to go to 2. So this right here, this vertical line is where x is equal to 2. I'm going to figure out where that blue line is, where the graph is, where x is 2. Well, there it is. That point right there is 2, 4. So when x is 2, y is 4. So our answer here is f of x equals 4. Okay, going on. Okay, same thing. We're going to continue. So this is, they used, instead of doing f of x, they decided to give it a different letter. Now we have h of x, but it's the same thing. They replaced x with 1, and so they want you to find y when x is 1. So x is 1 right here. Where is the graph where x is 1? I'm going to go up to the graph right there. When x is 1, y is 2. So that first question is h of 1 is equal to 2. Okay, now they said find x for which h of x is equal to negative 2. So just keep in mind that the f of x, or in this case h of x, is y. They're saying y is equal to negative 2. Find x. So find x when y is equal to negative 2. So when y is equal to negative 2, it's right here. And luckily, the graph actually goes through that exact point. So that point is 0, negative 2. So when y is negative 2, x is 0. Another point, just for another example, another point for when y is negative 2 would have been 3. Because this other point, this other point, 3, negative 2, when y is negative 2, x is 3. So that would have been another answer for that problem. Okay, finishing up here, we're almost done. So now we have a function table. So to fill out a function table, all we really have to do is take these values for x and substitute them in to the function to find what y is, right? So the function is 3x minus 1 is equal to y. So if I want to find out what y is when x is 1, I'm going to replace I'm going to substitute x with 1 and then simplify using my order of operations, right? My PEMDAS. So I've got 3 times 1 minus 1 is equal to 2. Okay, moving on to 3. I'm going to substitute, replace the x with 3. And now I'm going to do 3 times 3 minus 1 is 8. And then I'm going to do that for the rest. So I've got the next one is 3 times 7, which is 21, minus 1, which is 20. And 3 times 10, which is 30, minus 1 is 29. Okay, and lastly, very similar to the last question, but this time it's written with function notation, which is just a fancy way of writing y, right? So we're doing the same thing. I'm taking this function, which is equal to f of x, which is the same as y, to find what y is. I'm going to substitute x with these values for x. So I'm going to replace x first with negative 3. So that's 4 times negative 3 is negative 12. Negative 12 minus 2 is negative 14. Next one, 0. I'm going to substitute the x with 0. That'll be 4 times 0, which is 0, minus 2, which is negative 2. Okay, next one, we've got 2. I'm going to replace the x with 2, and that's going to be 4 times 2, which is 8, minus 2, which is 6, right? Okay, the next one would be 4 times 4, which is 16, 16 minus 2, which is 14. And the last one is 4 times 5, 20, minus 2, which is 18. All right.